So the subject code is EC3552 VLSI and chip design, and unit 1 is about MOS transistor principles. In the previous video we have discussed about MOS logic families, and in this video we are going to discuss about ideal and non-ideal IV characteristics. So in this particular video deals about ideal and non-ideal IV characteristics. First we will see about ideal IV characteristics. So the ideal characteristics, that is the MOS transistors, have three regions of operation. Number 1, cutoff or subthreshold region, linear region. Number 3 is saturation region. The current and voltage, that is the I and V, for an NMOS transistor in each of these regions are going to be considered. The model in this characteristics, it assumes, this is the main point, this ideal characteristics, this is the main point, it assumes that the channel length is long enough that the lateral electric field, that is the field between the source and the drain, is relatively low. Because of the long channel, the field is low, which is no longer the case in the nanometer devices. This model is variously known as long channel, ideal, first order, Shockley model. So these are all the three regions we are going to discuss. So first is the cutoff region. Here there is no channel, that is the drain to source current is 0, and figure B and C deals about the linear region of operation, and figure D represents the saturation region. That is the pinch off channel is pinched off, IDS is independent of VDS. So let us see about each of these. First we will see about figure A. So figure A, this is, let us see. In figure A, a negative voltage is applied to the gate, so there is negative charge on the gate. The mobile positively charged holes are attracted, that is the holes are mobility. So they are attracted to the region beneath the gate. This is called the accumulation mode. So next we will see about the figure B. So here it is attracted, and in figure B, a small positive voltage is applied to the gate. In previous case, we are applied negative voltage to the gate. But in the next case, we are going to apply the positive voltage, small positive voltage to the gate, resulting in some positive charge on the gate. The holes in the body are repelled from the region directly beneath the gate, resulting in a depletion region forming below the gate. Next, we will see about the figure C. Figure C, we are going to increase a higher positive voltage to the gate. So initially 0 voltage or negative voltage to the gate, less positive voltage to the gate, figure B, and figure C we are going to increase more positive voltage to the gate. So when it exceeds a threshold voltage VT, then attracting more positive charge to the gate, the holes are repelled further and some free electrons in the body are attracted to the region beneath the gate. This conductive layer of electrons in the p-type body is called the inversion layer. The threshold voltage depends on the number of dopants in the body and the thickness, that is T-ox, OX, suffix ox, of the oxide. This parameter is important. We are going to use in the further derivations. It is usually positive as shown in this example, but it can also be negative, that is the thickness can also be negative. Next, the figure, before figure we show it is an NMOS transistor. The transistor contains a MOS stack between the two N-type regions called the source and the drain. Okay, two stack, one side is source, another side is the drain. So here in the first case, figure A, all further we will discuss the figure A. Okay, so in this figure A, the gate to source voltage VGS is less than the threshold voltage. The source voltage is grounded. The junctions between the body and the source or drain are zero biased or reverse biased. So a little or no current flows. We say the transistor is off, and this mode of operation is called the cutoff. It is often convenient to approximate the current through an off transistor as zero, especially in comparison to the current through an on transistor. However, that small amounts of current leaking through off transistors can become significant, especially when multiplied millions or billions of transistors on a chip. Next, here we are going to increase the positive voltage to the gate compared to the figure A. So when we increase the gate voltage more than the threshold voltage, So now the inversion region of electrons, that is the majority carriers called the channel, connects the source and the drain. Here the majority carriers, N means majority carriers are electrons. It creates a conductive path and it makes the transistor on. The number of carriers and the conductivity increases with the gate voltage. If gate voltage is more, then we have more carriers, and so conductivity also increases. The potential difference between the drain and source is VDS, which is nothing but VGS into VGD. If VDS equal to 0, that is both are equal to same. Actually here it is minus. VGS minus VD. There is no electric field tending to push the current from drain to source. When a small positive voltage VDS is applied to the drain, current IDS flows through the channel from source to drain. This mode of operation is termed as linear, resistive, triode, non-saturated or unsaturated. The current increases with both the drain voltage and gate voltage. If VDS becomes sufficiently large, next case, if VDS is sufficiently large, that is even gate voltage is less than the threshold voltage, now the carriers will be less. The channel is no longer inverted near the drain and it becomes pinched off. That is the last figure. However, conduction is still brought about by the drift of electrons under the influence of the positive drain voltage. As electrons reach the end of the channel, they are injected into the depletion region near the drain and accelerated towards the drain. Above this drain voltage, the current IDS is controlled only by the gate voltage and ceases to be influenced by the drain. This mode is called saturation. Finally, let us summarize the above principles. That is, the NMOS transistors has three modes of operation. That is, if VGS is less than the threshold voltage, the transistor is said to be in cutoff, that is off state. When VGS is greater than VT, that is the threshold voltage, the transistor is turns on. If VDS is small, the transistor acts as a linear resistor in which the current flow is proportional to VDS. Next case, if VGS is greater than threshold voltage and VDS is also large, the transistor acts as a current source in which the current flow becomes independent of the VDS. Next, the PMOS transistor, it operates in just the opposite fashion. That is, the long channel model assumes the current through an off transistor is 0. When a transistor turns on, that is VGS is greater than VT, the gate attracts carriers to form a channel. Next, this ideal equations can be summarized like this in three regions. So that is, the drain to source current IDS will be 0 in the cutoff region, and the value is like this when it is in the linear region, and the value is like this when it is in the saturation region. Next, the electrons drift from the source to drain at a rate proportional to the electric field between these regions. Thus, we can compute the currents if we know the amount of charge in the channel and the rate at which it moves. Thus, the charge in the channel that is given by represented by Q suffix channel. It is given as, charge is given as capacitance Cg into VGS minus VT, where Cg represents the capacitance of the gate to the channel and VGS minus VT is the amount of voltage attracting charge to the channel beyond the minimum required to invert from P to N. The gate voltage is referenced to the channel which is not grounded. If the source is at Vs and the drain is at Vd, then the average is represented like this. So, average means Vs plus Vd by 2. Therefore, the mean difference between gate and the channel potentials, that is VGC, is represented by Vg minus Vc. It is also represented in this figure. What is Vg, what is VGD, Cg, everything it is represented, and that parameters is also clearly displayed in the figure also. Also, we can model the gate as like a parallel plate capacitor, which is the capacitance is directly proportional to the area over the thickness. For example, if the gate has a length capital L and width W and the oxide thickness is T ox as shown in this below figure, the capacitance we can write like this, where E permittivity epsilon OX is the permittivity of the free space, and the value is given like this, and the permittivity of SiO2 is given this like this. So often this aux by Tox term we are calling as Cox, the capacitance per unit area of the gate oxide. Next we will see each carrier. What is the, we are going to define the mobility, the parameter mobility. Each carrier in the channel is accelerated to an average velocity mu proportional to the lateral electric field, that is the field between the source and the drain. Now the constant of proportionality mu we are defining as mobility. So that is mu equal to mu times E. The time required for the carriers to cross the channel is the channel length divided by the carrier velocity, capital L divided by mu. So mu represents the mobility, capital L represents the channel length. Next, therefore the current IDS, IDS, that is between source and the drain, is the total amount of charge, we know, no, Q channel, total amount of charge in the channel, which is divided by the time required to cross. So that is L by V. So and when we substitute, we get like this. The term VGS minus VT arises, and it is also can be abbreviated as capital VGT, and K slang is represented as mu Cox. If VDS, first case let us consider, if VDS, the drain to source voltage, is greater than saturated drain voltage, that is VGT, the channel is no longer inverted in the vicinity of the drain. We say it is pinched off, higher voltage. Beyond this point, called the drain saturation voltage, that is increasing the drain voltage, has no further effect on the current. When we substitute VDS equal to VD sat at this point of maximum current in the above equation, we find an expression for the saturation current. Now we are going to derive an expression for saturation current which is independent of VDS, that is the voltage, it is independent, and the expression is given like this. And this expression is valid only for when VGS is greater than the threshold voltage and VDS is greater than the drain saturation voltage. Thus, a long channel MOS transistors are said to exhibit a square law behavior in saturation. In the expression we get V square GT. Here we can figure two figures of merit, that is I on and I off. I on is also called as drain saturation current. It is the on current, that is IDS, when VGS equal to VDS equal to VDD. And we can have one more parameter I off. It represents the off current when VGS equal to 0, VDS equal to VDD. Next, according to the long channel model, I off equal to 0 and I on equal to beta by 2 into VDD minus VT. Next, we will move on to the non-ideal characteristics. The Shockley transistor model, which we derived a current voltage expression, IV expression for an ideal transistor, is failed because of many characteristics. So we can have the following non-ideal IV effect. Number 1, mobility degradation, velocity saturation, body effect, drain induced barrier lowering, channel length modulation, subthreshold conduction, gate leakage. So first we will see one by one in detail. What is mobility degradation? We derive an expression for mobility. Mu equal to mu times C, where mu is the carrier drift velocity and this mu is the mobility. The mobility term in the above equation, which we assumed to be the independent of the field capital E. This is the reasonable approximation when the electric field is weak, but it breakdowns for a stronger electric field. Stronger vertical electric fields can attract the charge carriers traveling along the inversion layer and cause it to collide with the oxide interface. This effect causes mobility degradation, whereas the effective mobility decrease with increase in VGS. Next we will move on to the velocity saturation. Under strong lateral electric fields, the charge carriers are accelerated and the collisions between the charge carriers and the silicon lattice increases. Beyond a certain level of electric field, the carrier drift velocity saturates at mu sat. This is called velocity saturation. Note that transistor saturation and velocity saturation are two different phenomena, but both of them result in the saturation of current through the channel. That is with respect to VDS. Now we already know mu equal to mu E, where E represents VDS by L, where L is the length of the channel. With the decrease in the length of the channel, the effective electric field for the same VDS also increases. With increase in the strength of the electric field, the charge carriers of a short channel device becomes velocity saturated at a much lower VDS as compared to a long channel device. So this can be evident from this graph. So in the graph, if we see, the long channel device have a linear relationship between IDS and VDS, and until the condition, it should be VDS is equal to VGS minus VT. But after this condition, the long channel enters into a saturation region. Next, consider the short channel device. Next graphs, this lower below line. In the case of short channel device, it enters into a velocity saturation much before the drain of saturation region. In short channel devices, depending upon which is lower than VDS sat, the device can go into the velocity saturation or drain pinch off saturation. If VDS sat is smaller, then the short channel device enters into velocity saturation first. If VGS minus VT is smaller, it enters into a drain pinch off saturation first. So here we have two saturation. One is drain pinch off saturation, another one is velocity saturation. So according to the condition, it either enters into any one of these saturation. Next we will see about body effect. So far we have considered about that the source and the body terminals are both connected together and into the ground. But what if the body is not connected to the source? If the body is not connected to the source and it is connected to a different potential, then this causes the threshold voltage to vary according to the below formula. So the formula is given below, where Vt0 is the threshold voltage and Sb is equal to 0 and mu is the body effect coefficient and phi s is the surface potential at the threshold. So from the above formula, we can infer that the threshold voltage increases with the source voltage and decreases with the body voltage. Next non-ideal characteristics is drain induced barrier lowering, DIBL. The drain and the body form a PN junction. If the voltage on the drain is positive and the voltage on the body is 0 or negative, then this PN junction is reverse biased. With increase in VDS, this reverse bias keeps increasing. With increase in the reverse bias, the depletion region also increases its size and start infringing on the channel. The depletion region is devoid of mobile charge carriers, that we know, and so it occupies a part of a channel during the high VDS voltages. This means that the gate voltage has less of the channel to deplete. That means a portion of the channel is depleted by the depletion region. As a result, we know the threshold voltage decreases. However, this effect is not very prominent in the long channel devices because their channels are very long with respect to the length of the depletion region. However, the short channel devices have shorter channels whose lengths are comparable with the length of the depletion region, and so the short channel devices have DIBL effect as a prominent. But in ideal characteristics, we assume the channel length is so long, so we are ignoring all these parameters. But when we have a short channel devices, this DIBL effect is also high. Next, we will see or how in the case of long channel device, and B represents a short channel device and the corresponding depletion length coefficient with the respect to the channel. Next, we will see channel length modulation. As we know, VDS increases, the depletion region also increases and the channel length becomes shorter. The current through the channel is inversely proportional to the length of the channel. With the decrease in the channel length, the current also increases. Just like the DIBL effect, this effect is also most prominently seen in the short channel devices as opposed to the long channel devices. Incorporating the channel length modulation, the current equation for the saturation region becomes like this. The equation is given like this, where lambda is the CLM, channel length modulation parameter, that is the Next, non-ideal characteristics. And for long channel it is negligible, and for short channel it is more prominent. Next we will see the sub-threshold conduction. So far we are assumed that the drain source current is 0 for VGS is less than threshold voltage. But current doesn't cut off abruptly once VGS becomes less than the threshold voltage. As VGS decreases below the threshold voltage, IDS also decreases exponentially. It is exponentially. If we were to plot a logarithmic plot of IDS versus VGS for VGS less than VT, it would be a straight line. This effect is called the sub-threshold conduction, and this effect is exacerbated by the DIBL effect. So it is not a suddenly the IDS is not 0, it is exponentially decreasing. So, and this graph, this effect is also shown here. The region below VT is called the subthreshold region, and the IV characteristics for two different VDS is shown here, and both the plots have a non-zero current in the subthreshold region, but VDS equal to 1 plot has a higher current due to the DIBL current effect. Lastly, we will see about the gate leakage, the gate and the channel. As we know, it forms a capacitor. No current should pass through the capacitor ideally, but with the decrease in the oxide thickness between the gate and the channel, the electron tunnel across, and this constitute the gate leakage current also. So we cannot ignore the gate leakage current. So the gate leakage current for different values is plotted here. So the gate leakage current versus VDD for different values of oxide thickness. So okay, it is very clearly shown, and the gate leakage current can be reduced by substituting the silicon dioxide with a higher dielectric constant material. So in order to overcome this gate leakage current, we can use this silicon dioxide layer. So all these content I have referred from this book Neil H.E. Waste as prescribed in our syllabus. Thank you.